Were there questions on the propagation of uncertainty stuff? I know, so I had 2 questions on email about the uncertainty with the parentheses. And so I can go over that real quick just as a refresher. Did you understand my email, I think? Yeah, okay. So, whenever you write the parenthesis way of writing uncertainty, see, where's my pen? There we go. Let's say we write, the mean is 123.456 in parenthesis 3, say grams, okay? So that parenthesis is telling us where the uncertainty is, and it's put next to the place value. So we're saying that, think about the significant figure convention in the sense that we keep all the certain digits plus 1 uncertain digit. And I always say 1 or 2, not 3, but 1 or 2. So these are certain, and this is uncertain. And so that's where this uncertainty goes, right there in that digit. And it's not plus or minus 1 in the uncertain digit, like we assume for the significant figure convention. It's plus or minus 3. So we have more information when we have a standard deviation. So in this case, we've done multiple experiments. We have an average, and we have a standard deviation. So the standard deviation is equal to 0.003 grams. So all that information with this is captured just with the parentheses. Does that make sense? Okay. Now, if they have 2 digits, it replaces, it tells you there's 2 uncertain digits next to it. So if this were x bar equals 123.456, let's say we had a 25 in there, then our S would equal, and so this is telling us we have 4 certain digits and 2 uncertain digits. And we know that because there's 2 digits of uncertainty given. So it's just whatever those last 2 digits are, that's the place value. The 5.6 is meaningless. It's just the place value that's important, and it's replaced with 25. So we would say the standard deviation is equal to 0.025 grams. Okay. I've seen both. I've seen 1 digit and I've seen 2 digits, but 3 digits I've never really seen. So I would say 3 digits, if you're uncertain with 1 digit, sometimes it's helpful to show that your uncertainty wasn't quite as high as 3, it was 25. So, is that giving us more information? A little bit. It's giving us a bit of a guard digit for rounding in the future. But so I've seen 25, but the 3rd digit is totally ridiculous, So we just don't even have 3 digits of uncertainty, but we could have 2, as long as they match. And so wherever the rounding is, we would round this to that place value so that they match. So we would report 123.456. We would round there and report the uncertainty as 0.025. That's okay. Here we could, if we only had 1 significant digit of uncertainty, then we would keep it up to the 6, and we would round there because this is telling us where we're uncertain. Okay. So that's the main questions that I had on the propagation of uncertainty. So go through that video. It talks about RSD and coefficient of variation and all of those different statistical terms that we'll be using. You'll get a good review and practice of that when we get into the calibration curves and calculating the uncertainty in the calibration curves. And so you definitely need to watch that video and be good with it to do the homework this week, but also we're going to use it when we get to calculating the uncertainty of the calibration curves. Okay, so let's jump into today's lecture. So remember the measurement exercise. Everybody had the little blue disc and they were measuring with the rulers. Let's say we had a new hire. So we've got a forensic chemist that we've hired a trainee. So the trainee comes in, they've been through their training, they're ready to make measurements and so on. And so we give them a known or at least a sample that we have an accepted value for. And we give them both to the trainee and to the forensic chemist and see how they both do. Do they have the same average? Do they have the same standard deviation? And so here to hold the lecture today, we're comparing 2 employees to see if the trainee needs to be retrained or check their technique or something like that. if they're accurate, if they're precise, and so on. So we're training a newbie at DW Labs. We have a forensic chemist. We also want to recertify on the equipment. We went to the vault, and we have a recent seizure that's been well characterized, and it has 13.2% cocaine by mass in the little baggie or whatever. So we take out samples and we give it to both of them, and they don't know. They don't know how much is in there. So we ask them to analyze it. Okay. So we ask them to analyze it 10 times. Are they accurate? Are they precise? And here's the most important case. Are they the same as or different from each other? Because we really, as a lab manager, I don't want to have to worry about which employee I give the sample to. Does that make sense? We want everybody to at least give the same answer when given the same sample. Okay. And to be reliable, like your technique is as good as your technique. So precision is important. So in a perfect world, there'd be no statistically significant difference in accuracy, which would be the means of their results. They both analyzed 10 times. Their means should be the same, but they're never going to be exactly the same. So we need a statistical test to determine if they're the same. And so we'll do that today. That's the t-test. And then there shouldn't be any difference in their precision, right? One shouldn't have a standard deviation this wide and the other this narrow. And we'll use the f-test to determine that. I mean, they're never going to be the same exactly. So how different is too much? That's the f-test. Okay, so between the lab personnel, we should be able to get comparable results. They won't be the same, but they should be comparable. So here's the data. It's always good to look at the data to see if there's an acronym for everything. In my training for Six Sigma, they called it ANOG, and it's the stupidest acronym ever. And so they do ANOG on your data first, and we're like, what is that? It was analysis of good. Is the data good? Okay, that's just common sense. Look at the data and see. We gave everybody, a 13.1 percent cocaine sample, and everything's around 13.1. There's some 12 nines and a 12.6. Oh, here's an 11.5. Ooh, here's a 15. But still, in general, they're all around the right answer. We would just stop there if we had 130, 160, or 1%, 2%. We would say, all right, we're so far off. Let's check to make sure you actually got the right baggie. Oh, you're testing the desiccant. No, that's not cocaine. Give me that. Right. So there's things that could happen to just make the data. Don't waste your time doing statistics when it's just totally bogus. Okay. So we look at this and we're like, okay, this looks fine. Okay. So we could plot the data and compare them side by side. And so this is called an individual data plot. And you can see the true value here. The bar is in green at 13.1. And then the plus or minus 0.1 was the uncertainty in our true value. So that's how well characterized our standard was. And so then we're looking at the analyst and the trainee. So are they accurate? What do y'all say? It's a yes or no. So I see some yeses. I see, definitely, is this one accurate? Yes. What's the blue dot, do you think? The mean, yes. This is the mean. The blue dot's the mean. And it's inside the bars of our standard, even. So we know the standard to plus or minus 0.1, and the mean of our forensic chemist is inside those bars. So that's good. So, yeah, for sure. What about this one? I mean, it's pretty close. It looks like it's coming in at 12.9. And it's got some spread, so it probably has some error bars on it, on this data, which incorporates the true value. So, yeah, I would say they're pretty accurate. Yes, because the means are close to, and I'll say XT. Right, the true value. I went and got a cold. I don't know how. But... Okay, what about precision? Are they precise? I see some of this. The trainees have got a problem, right? first of all, we've got one way out here. That's the 15. Everything else is down here, and you can see the mean is affected by these values down here. But this one, yeah, this is pretty good. This is only about 13.5 and 13.1. So they're pretty precise. So I'll say forensic chemist is okay because the scatter is low. Would you agree with that assessment? Just looking at the data, this is just individual data points. Now notice how much easier it is to look at it graphically than in a table. We had the table of data, and it's just numbers, right? So it's way better to compare things in a graph. So put them up on an individual value plot if you have access to Minitab, or you could plot this in Excel. You could have then use a line graph. So in Excel, this would be a line plot. Use markers, no lines, and a line plot, and then you could have the category of trainee, the category of forensic chemist, and then you would see the data on the y-axis straight above. So that would be something that would be easy to do. Okay, so this is the benefit of graphical methods. It's easy to compare two data sets. You can see differences in standard deviation and in the means. Now, there are some limitations in the graphical methods in that we can see that they're different, but we don't have a number on that. Like we don't really see on here the standard deviations. We don't have any indicator that that's an outlier or anything. So here's a different kind of graphical method. This is a box and whisker plot. Okay. All right, so here's all the things on a box and whiskers plot. You have the minimum value, and there's a line that goes down to the minimum value. There's a line that goes to the maximum value too, but there's also an outlier on this one. So max, non-outlier. So those are the whiskers. They go to the max and min, and they give you an idea of the range of the data. Now, what is this quartile business? Okay. This 25th quartile is the bottom 25% of the data. So you have 25% here, then another 25% between the 25th percentile and the median. That's another 25%. So this is the 50% part. Then you have another 25% to get up to the 75th percentile right here. And then when you get up to this, you're at the 100%. Your maximum value. So a few of you, and I remember some questions in PChem 1 about the grade book and Blackboard and so on, because there was a percentile column. I just put that in there for my own use to kind of look. It's not listed in the syllabus or anything. But whenever you see a percentile rank, that's what it is. It's a rank from the top data point to the bottom data point in percentages. So the 99th percentile, 99% of the data is below that point. So if you're wondering how you're doing in class, maybe you think you're like doing poorly because you got an 87 average, right? And then you look at your percentile rank and it's 95. You're like, I'm doing pretty good, right? Because 95% of the other grades in the class are below 87. Is that what I said, 87? Yeah. And so that's where the percentile rank comes in handy if you're looking at that. If you're looking at it and you're like, man, I got a 60, man, I don't know how everybody else is doing, and you look at the percentile rank and it's a 1%, you're like, ooh, 99% of the class is above my grade. That's a panic time. That's when you come knock on my door. What can I do? Early, right? Not at the last day. All right, so that's the box and whiskers plot. And then this is showing both the median and the mean. So the mean is still this dot right here. And the median. And the mean and the median will separate when you have skewed data. So this data is skewed to low values. And so if we were to kind of plot a histogram sideways, it would look like that. So this is skewed low, and we have a whole lecture on that. And that draws the median down and away from the mean. Okay, so we answered the same questions, accurate and precise. Now, accurate, you could say that they're the boxes. If the box contains the true value, then you can say it's accurate. Okay, so it's not the best because the mean and the median are pretty far away from the true value, but at least it's within the middle 50% of that data set for the trainee. And of course, the forensic chemist is great. I mean, that whole box even covers the uncertainty in our true value. Questions on the box and whiskers? Okay. There are little add-ons to Excel that allow you to just do these. Okay, so then let's look at some of the figures of merit. Okay, so a figure of merit is a generic term. You might write this down. Figure of merit is anything you're interested in. Okay, a figure of merit is a number that tells you something about the data. We already used a bunch of them, like mean. The mean is a figure of merit. The standard deviation is a figure of merit. What is it about the standard deviation that makes it a figure of merit? Well, you want low standard deviations, so lower is better. Okay. The mean may not necessarily be a figure of merit unless you have the accurate, like the true value. Then it would be the deviation from the true value. But you get my point. It's single numbers that tell you something about the data, and then you can compare those to things that are good. So we have the mean and average, and I've got all the Excel formulas here, and there's an assignment on Blackboard. I think it comes up in next week, where you do all of these, because it's one thing to just look at my notes and say, oh yeah, I could do that. But it's another thing to get in Excel and actually make all of these formulas and play around with them. Okay, so it's just basically this lecture you're doing in Excel on your own. Okay, and so just go through all the formulas are in here. Now these formulas, almost all cases, well in this case they're shown here for column C, but a lot of the cases they're shown over here for column B, and you just, it's the same formula over here, but it's all in column C. So just be smart about which column this formulas are referring to. Now you can do the range. Now it's easy to calculate the range in Excel by using the max and min functions. So this is saying the maximum, you open parenthesis and close parenthesis and put in the whole series. So C3 through C12. So you select the whole column and it's max. And it's gonna, no matter where that maximum is in the data set, it'll pull it out. And then you can subtract the min, and that's the range, max minus min. So you can build your own little statistical set of figures of merit here using these formulas. Standard deviation for samples, okay? So this is STDEV dot S. So dot S means for sample. That's going to be dividing by the n-1. If you have 15 data points or more, then you just do the population, and it'd be dot P. So dot P tells it to not divide by the n-1, and you get the population standard deviation. We have 10 of these, so we're going to use the standard, the sample standard deviation. Okay, so the question is, in terms of accuracy, does the average value, which is given there for both of these analysts, plus or minus the standard deviation, contain the true value? So here we have for the trainee, we have 12.9, that's the average, and this is the standard deviation, 0.9. So 12.9 plus or minus 0.9 goes, if we take the low value, so we subtract the minus part from 12.9, we have 12. And if we add it, it goes up to 13.8. And our true value is 13.2. So you see our error bars contain the true value. So you could say that, you know, the trainee could look at that and go, yes, I got the true value. I'm accurate. Okay. But look at the forensic chemist. It's even better. Okay. 13.3 plus or minus 0.2. So 13.3, if we subtract 0.2 is 13.1. And if we add 0.2 is 13.5. and our true value is 13.2. So this is great. They're both accurate in the sense that their error bars capture the mean of the true value. So that's great. Okay, so both seem to be accurate because their means and standard deviations contain the accepted value. However, what do we do with this 15? Okay, and over here on this one, I just conveniently made the max value in the same row. That's just me fiddling with it. Okay, but the max value happens to be in the same row. Just don't pay any attention to that. I just did it for convenience sake. Okay, but we have a 15 on the trainee, and our maximum value for the forensic chemist is 13.7. So let's analyze those two data points. So to do that, we need to talk about hypothesis testing. So every time you make a decision, specifically statistically, you need to decide whether it's operating normally or there's some special problem. We call it special cause variation. Okay. And so our null hypothesis for all of the examples today, I'm going to list them all out, and then we're going to go through one. So the first thing we're going to test for is that 15, is it an outlier? So the normal operation when you're measuring data is that it's not an outlier. So your null hypothesis tries to capture the normal situation. Okay, it's your baseline assumption. Your assumption is it's not an outlier. Okay, so that's why we call it the null hypothesis. Null is another word for zero, and so it's your zero starting point, your H0. Okay, or people call it HO, but it's H0 actually. And we can be correct in that if we fail to reject it and it's not an outlier, or we could be correct if it is an outlier and we do reject it. But we could also make two mistakes. Let's say it really is an outlier and we fail to reject it, then that's a type 2 error. Okay, so you see here, if HO is false, that means it is an outlier and we failed to reject our null hypothesis. That's a type 2 error. Okay, so that would be a false positive, right? So it is actually negative and we say it's positive. Okay, that's a false positive. Here, reject the null hypothesis when it's not. That's a false negative. It really wasn't an outlier, but we said it was. So this is where we get those terms of false negative and false positive. Okay, here's another hypothesis we're going to test today. The trainee and forensic chemist data sets are from the same population. So that means they have the same means. So we have an overall population in this little baggie that we measured, and they both measured the same samples. Did they get the same answer or not? Are they both measuring the same thing? So that's the baseline assumption. We assume they're measuring the same sample, and the data suggests maybe that they're not. Okay. Is that really the case, that they're measuring two different baggies, or that the trainee is just not as reliable in their testing? Okay. Then the third null hypothesis we're going to test today is the trainee and the forensic chemist data sets have the same variance. We talk in terms of variance a lot of times in statistics, but in chemistry we really focus on standard deviation. But the variance is just the standard deviation squared. So they go together. So if they don't have the same variance, that means they don't have the same standard deviation. So they're not the same precision. Okay, so let's talk about this rejecting the null hypothesis or not. Okay, it's kind of interesting. We have a really rigid bar to reach in order to reject the null hypothesis. So if the probability, and this p-value is something we're going to really focus on in this course, this p-value, let me find it, is this right here, the probability that HO is true. So a lot of times you'll see like P equals 0.12, okay? That's greater than 0.05, okay? And so that what we would do is, if you look at this if-then statement, if the p-value is less than 0.05, then reject the null hypothesis. So what is this? This is the probability that the null hypothesis is true. So remember, the null hypothesis is everything's behaving as we expect. And if it's even 6% chance that it's behaving as we expect, we're gonna keep it that way. We're gonna accept that the system's working. We need at least a 5% or less than 5% chance that the system's behaving correctly to reject it. Okay. So if the probability is less than 5% that the null hypothesis is true, then reject it. Okay. This 0.05 is called alpha. So put that in your terms, circle alpha. You'll hear me say stuff about alpha. You'll read it too. The alpha value is your sort of level of discrimination in terms of your null hypothesis. And we typically keep it at 0.05 because 1 minus alpha is your confidence. So we also talk about 95% confidence intervals. That's 1 minus alpha. So if 0.05 is your alpha, you're working at 95% confidence. Now, 95% confidence isn't great. That means it's 1 out of 20 will be off. That's not very good. I mean, would you want that for your mail? Like 1 out of every 20 letters is lost. Okay. I wouldn't want that for, surgical procedure, right? But in forensics, okay, why is it acceptable forensics? Well, because we have multiple techniques that are all operating on a 95% confidence at least. So we have an FTIR, we have a GC, we have a mass spec, and all of those independently would be held to a 95% confidence. So if you miss all three randomly or some strange thing got over, it would have to be a 0.05 chance to get by this instrument, 0.05 chance by that instrument, 0.05 chance to that instrument. So what is 0.05 to the third power? Okay, 0.05. Yeah, so it'd be 1 chance out of 1,000 that it would get through all three of those. Let me make sure I did that right. Yeah. No, one chance out of 10,000. Okay, that would random error at 5% would get past all three techniques and give you a mistake in the result. Okay, if there was something that far off, your little brain up here and your observation skills would probably pick up on something, So if you can't state your null hypothesis clearly and concisely, then you have no business doing statistics because you're using p-values in statistics. And if somebody were to ask you, what does that p-value signify? You don't want to stand up there and go, it's the probability value. And they're like, probability of what? Probabilities are probabilities of events. What is the event you're talking about? And in our case, it's the probability that the null hypothesis is true. And then the follow-up question is, well, what is that null hypothesis? Let's do the outlier. Well, the null hypothesis is it's not an outlier. Okay. So if there's a 6% chance that it's not an outlier, then we're going to say it's not an outlier. If there's a 4% chance that it's not an outlier, then we're going to say, it's probably an outlier. We're going to reject that null hypothesis that it's not an outlier. So let's do that. Let's do the Dixon's Q-test on this. This is how we set up the Dixon's Q-test. Now, before we get into this, if we look at that number 15 that the trainee did, and we say, do you have any information on that value? Because we're about to do statistics on it. If we're going to do statistics, the null hypothesis is it's not an outlier. But if we ask the trainee, was there anything funny about number 8 or whatever it was? And they say, oh, yeah, the pipette tip popped off right when I was about to pipette into the thing. Well, did any get in there? I don't know. I got a new pipette and I pipetted a new sample into that vial. There's something wrong. Okay, so you throw that one out no matter what because you know it's not the same as the others. So if there's any explanation as to why that data point might be suspect, then you have a reason to throw it out. Okay, and it should have been thrown out before you got to the analysis, not to the end. So statistics isn't meant to be used to get rid of data points that you already know are bad. Right? Because the null hypothesis is it's not an outlier, but that's the one that had the pipette tip fall out and it's screwed up. You know it's screwed up. So your null hypothesis is bogus. At that point, you don't even need statistics. Okay. So if you tip over the vial and you don't think anything fell out, you don't think, do another one, or go with 9 samples instead of 10, okay, and write a note in the notebook. Okay, and so this is the way we do this. Dixon's Q-test and also the Grubbs test, which we'll do next, are used when there are no known reasons for an outlier data point. And so we always have 2 values. We have the critical value and the experimental value. So the critical value comes from the table down below. And you can find the reference down here at the bottom where this came from. But anyway, you have the alpha here, okay? And so this is just showing you that you have the different, Q values at 95%. So we're looking at alpha 0.05. And then we have a number of values that we look up. So here's the value for 10. And so here's our Q critical for this particular analyst or analysis, 10 values. Okay, so Q crit equals 0.466. And then Q experimental is calculated this way. We have the range here, and then we have the gap. So this gap can be on the high side or the low side. It's the questioned data point minus the nearest neighbor. So if you have a number line, and let's say you have 3 values on there, you've got a mark there, and a mark there, and a mark way up here. The average this might be the mean, right? But it's not asking for the mean, it's asking for the gap. It's asking for this distance to the nearest neighbor. Okay, and it's comparing that distance to the range. So it's really a ratio of the range. How much of that range is this first gap? If it's too much, then it's going to be higher than the critical value, and we're going to say that that's an outlier. It doesn't represent the data. And you can look at my example with the x's. That doesn't really represent the data. It's way over there, and you've got 2 points over here. Okay, but if you have 3 data points, 97% of that range has to be made up by the gap. So those 2 data points have to be really close and have one way over here for Dixon's Q-test to throw it out. Okay. If you have 10, then it's a little bit easier scale. You have 9 data points here that are pretty close together, and you got a 10th one way over here. If more than 46% of that range is just that gap, then it's an outlier. We'll apply it in a minute. So we did it in Excel. So this is the Grubbs test, or the Z transform. This one has a little bit more use. This, if you'll notice, this other one is one favored by chemists because it's in the analytical chemistry literature and so on. It was introduced to me by this book, Skoog, West, and Haller, Fundamentals of Analytical Chemistry. That was my quant book in my undergrad days. So you still see the Q test, but I think it's been kind of replaced by the Z transform, or the Grubbs test, which is the next one. This one kind of assumes normal statistics or Gaussian statistics, the normal distribution, and it has the mean. So you calculate the mean and you calculate the standard deviation. And so you're taking the questioned data point, that was that 15, and you're subtracting the mean. So you're seeing how far away from the mean it is in terms of number of standard deviation units. Okay, so it's sort of this gap per standard deviation. So we're transforming it into standard deviations. If it's 3 standard deviations away, it's probably an outlier. If it's only 1 standard deviation away, it's probably not an outlier. Okay, and the 0.05 level is at 1.96. So if it's almost 2. So if it's 2 standard deviations away, it's an outlier at 95% confidence. So again, it's used when there's no known reasons for throwing the data point out. It's based on a Gaussian distribution that has a mean of 0 and a standard deviation of 1. And you compare your Z value to the cutoffs or critical Z values. And so this is a number right here, this Z value for 95% confidence. You should know this one. Because that's also the number we multiply our standard deviation by when we're making 95% confidence intervals. Okay, and so when we have 95% confidence intervals, those error bars are set at plus or minus 1.96 times our sigma. And if we have a point that's 2 away, then it's outside our error bars, meaning it's an outlier. It's not part of this population. Okay, so let's look at these values. And so here's our nearest neighbor, and here's our maximum values. And so we have for the let's do Dixon's Q-test first. So this is 15 minus 13.3, okay, divided by the range, and so that gives a 4.86, okay. And then from that table for 10 values, our Q critical was 4.466. So 486 is greater than 466, and so this Dixon's Q-test is showing that that's an outlier. For the Grubbs test, 15 minus the mean, which is 12.9, so we take that difference, and then we divide by the 0.93, we get 2.3 as our Z value, and that's greater than 1.96, okay? So that's an outlier. Now, actually, it's surprising, even though 13.7 is close to 13.5, we take that minus the mean and divide by the standard deviation, which is really small, we get 2.15. So we didn't even notice that might be an outlier. But here the Grubbs test is telling us it's an outlier because it's greater than 1.96 when we do this Z transform. Okay, as far as the Dixon's Q-test, we do 13.7 minus 13.5, and then we divide that by the range, 0.6, and we get 0.33. We compare that to Dixon's Q critical value of 4.66, and it's not an outlier. So we have kind of a mixed decision on the forensic chemist, and we have a unanimous decision on the trainee that 15 is definitely an outlier, both with Dixon's Q and Z. Whenever we have this sort of mixed decision, I would favor keeping it because, again, we want to be conservative in our data. And so providing an estimate of your uncertainty in the worst case scenario is better communication than overly, you're going to catch more mistakes if you have a wider uncertainty. You're telling people, I'm confident at 95% that my error bars are here. You don't want to artificially shrink them. Okay, so we got a mixed decision on this, so we'll keep that data point of 13.7 in our forensic chemist. There's specific times when these tests fail, and that's when you have three values. So these have problems. When you have several data points with the same value. So if you have 13.1 and 13.1 and 13.2, okay? So I've measured something 3 times, and 2 of those numbers are exactly the same, and then I have a third number. This one's always going to show up as an outlier because the range and the gap are the same, right? So it's Q is going to give 100 or it's going to give 1 for that. The gap and the range are the same. So whenever you have data points that are coincidentally the same, and then you're testing that third one for an outlier, you're going to get yes every time. Okay. The way to solve that is, are you really sure that both of those are 13.1? I mean, where's that uncertain digit coming from? Is this a digital scale that's not precise enough to do this measurement, or what? So look at your data and make sure you're not rounding. If you round it too harshly, then you end up with situations that mislead you, and you start saying things are outliers that really aren't outliers. Okay, so that's just a caution. Okay, so our accuracy and precision without the outlier, with and without actually. So here we have the median and middle value. What's the accuracy? So this is our absolute error. So here's our mean, 12.9, okay? And we know 13.2 is our true value, okay? And so we are 0.33 low. Okay. So absolute errors have signs, positive and negative. Percent errors can too, I guess. But notice this is the absolute error in the scale of percent cocaine. Now this is the percentage of 13.2 that is in question. I mean, this is an example out of the book, and I wish they had used units, not percent by mass, but like milligrams per liter or something like that, something that wasn't percent. Because in this example, again, I took it out of the book, we get confused between percent cocaine and percent error. Okay, so this is how we calculate that percent error. We take the mean and subtract the true value. So that was the 12.9 minus the 13.2 and divide by 13.2 times 100%. You see it's a ratio of the true value. We're like, how much of that true value are we off? We're off 2.5% of the true value. Does everybody see that distinction? We're not off 2.5% cocaine. We're off 2.5% of the true value. Okay. I realize that can be confusing, okay, because we have two different kinds of percent. So if you always just add that extra word, the top one is the true value is percent cocaine, and the relative error or percent error is percent of the true value that we're off. Okay, so then what about this idea of this fairly accurate or whatever? This is my experience in terms of how people talk about uncertainty. This isn't in any book that I've found, but whenever people talk about, good, fair, poor, or whatever percentages, this is what I've come to sort of land on. Okay, if your percent error is less than 1%, that's excellent. Okay, if it's 2%, 1 to 2%, that's good. Okay, if it's up to 4.9, it's fair. So if you can get it within 5% of the true value, that's fair. Okay, if it's greater than 5%, it's poor. It's like you're 6% off of the true value. You could do better probably. But if you get it within 5%, that's pretty good. Okay, fair to good. Okay, let's look at some of the precision figures of merit. Okay, so here we have the standard deviation of 0.88. Okay, it says I use the population. I don't know why I did that, but that's what it is. Okay, so here we have the population standard deviation, and then RSD is that value divided by the mean. So 0.88% cocaine divided by 12.9% cocaine gives us 0.072. Okay. And so it's nice to convert that to percent to kind of see what percent of our mean are we uncertain. So this is me comparing my standard deviation with my mean. So of my mean of 12.9%, what's my error bar? Well, my error bar is 7.2% of that. So I can tell you I've got I've got $100 plus or minus 7.2%. So that's plus or minus $7. That's not too bad. I mean, I'm aiming at 100. It could be 93. It could be 107. Okay. So that's not too bad. And so, I mean, I have it at poor, but it's greater than 5%. I'd like to know within 5%. Okay. Now here's our confidence interval. This is that 1.96 times sigma. So that's that Z value at 95% times sigma. And so this 0.88 times 1.96 is 0.66. And then this is plus or minus that. So it could go as low as 12.2 and as high as 13.5. Those are my error bars at 95% confidence. Okay, if we take that outlier out, so let's get rid of the 15 and see how all these numbers improve. Okay, and one actually gets worse. So let's look. Okay, so we've gotten rid of the 15. And now that 15 was drawing our mean up. Now our mean has dropped to 12.6 because it was a high value. And now we're detecting a bias in our trainee. It's coming out low. So our percent error dropped down to 4.3% negative. It's almost hitting 5. So still, fairly accurate, but it got worse when we got rid of that outlier. And my word to you is, so what? Okay, you don't want to use this to determine if something's an outlier or not. That's a moral quandary that you need to pay attention to in your heart, because you'll be like, oh, my numbers got worse when I took that outlier out. Maybe I should erase that page. No, don't do that. Let the statistics guide you in reporting your results. Don't say my numbers got worse, so I'm going to undo that, because you don't know that. You won't know the true value. So you got to let your numbers be your numbers. Okay, so that's an important moral step there. Okay, now the precision got better. Okay, naturally, because we took out the outlier and the standard deviation shrunk from 0.8 to 0.5, and now it's 4.6%. And so that's still, between 2 and 5, so we call that fair precision. But we went up from poor precision to fair precision because we got rid of the outlier. Okay. Now the forensic chemist, these numbers are beautiful. Okay, 13.3 is the mean. We come down and calculate the absolute error at 0.07% cocaine. That's 0.5% of that cocaine value is our uncertainty. So that's fantastic. That's excellent accuracy. And then here's our precision. So 1.5%. So the standard deviation for the forensic chemist is 0.19. Again, that's going to be a RSD of 0.015 and 1.5% high, or 1.5% uncertainty, and that gives us good precision. Okay. So again, you have all of these equations that you can use in Excel. Put those in. You should be able to match the same numbers. Now, to report the standard deviation for our whole class, when we had the blue discs, we use the pooled standard deviation. And we need to use that here to test for the equal means. So we need the pooled standard deviation from the forensic chemist and from the trainee. And then we'll look at the difference in means divided by that pooled standard deviation. So here's that pooled standard deviation. And now we have really two situations. We have the trainee with the outlier and the trainee without the outlier. And then we have the forensic chemist. So we're going to do two comparisons just for grins. And so those numbers of degrees of freedom will change depending on if we have the outlier or if we don't. And then here's the t-test for the experimental value for the t. So we take the difference in means and divide it by the pooled standard deviation, because that's the standard deviation for the whole group. And then we have this factor of the number of data points that each person took. And so it'd be 10 and 10, 10 and 10 for if we kept the outlier. When we throw the outlier out, it'll be 9 times 10 and 9 plus 10 thrown in there. Okay. For the pooled standard deviation, it'll be 9 here and 10 there, and 9 here and 10 there. So you'll have 8 and 9, 8 and 9 when you subtract 1 from each of those. So here's the null hypothesis for the t-test. So the baseline assumption is the trainee and forensic chemist data sets are from the same population. They came out of the same baggie, we used the same instrumentation, and we should have gotten the same results. So the results should all be from the same population. So we calculate the experimental with this equation, and since our trainee could be high or low, we have a two-tailed test. This is one place where people screw this up. The training could be higher or could be lower. And so that's why we're taking the absolute value of the difference between the means, but we also need to cut our alpha in half. So 0.05 cut in half is 0.025. That's the alpha for the high or the low t-test. Since we're taking the absolute value of the difference in the means, we're really just going to compare it to the high t-test value. And then we're going to use the degrees of freedom for the trainee of 8. And so then if T experimental is greater than T critical, we reject the null hypothesis. And you can find t-test tables online. Here's an example of one. But you could also calculate it in Excel right here. So minus the outlier. Now, when you have the trainee with the outlier, then you have all 10 data points. That would be a 9. You put a 9 in there. So you could just calculate this T critical value using Excel. Then you don't have to go out on the internet and find some table and not know where that table is from or if it was actually what you're looking for. So this is the better way to do it. Okay. And so here we have the trainee. And so here we've got the pooled standard deviation, and again, calculated 2 different ways. This one was using all the data set, and then here's the trainee without the outlier. So this one right here was with these 8s and with these 9s. It was 8 times 9 divided by 8 plus 9, right? And then the same here for the t-test. This would be, again, 9 and 9. Now, I don't know why, like in the pooled standard deviation, it uses degrees of freedom, but in the t-test equation, it uses data point numbers. That's kind of a weird thing, right? In the pooled standard deviation, it's N1 minus 1, N2 minus 1, N1 minus 1, N2 minus 1. But in the t-test equation, it's N1, N2, N1 plus N2. So you got to pay attention. Are we using degrees of freedom, which is the number minus 1, or are we using just the number? Pay attention to the equations, and that's another place where people can mess this up. So here's our T experimental. Yeah, so this is T EXP, and here's T critical. So we got 2.83 for the trainee, and T critical is 2.67. So that's higher, so that means they're from different populations. And this one is even more higher. It's a 6.74 and 2.75. So in both cases, the T experimental is greater than the T table or T critical value. So it's saying the means are not the same. So that means our lab has a problem because the result depends upon who I give the data to or the sample to. And so we want to make sure that our 2 employees pass sort of a t-test, that when they do the results and it takes into account standard deviation, the pooled standard deviation is small and there's not much difference between their means, then it doesn't matter who I give the sample to. They give me the same result, plus or minus whatever is expected from the normal population variability. Okay, so now we do the F-test. Before we go on, are there any questions about what we just did? Hopefully you get more comfortable putting these equations into Excel. That's why I have you do this. Because again, watching me do it up here and showing all the results on the screen, your brain's not really engaged. I get it. It's kind of like watching coach shoot free throws. Okay, you can't be on a basketball team and watch coach shoot 50 free throws in a practice and think that you're going to be okay on the line and under pressure. Okay, so you need to do it yourself, even if it's something that you you're going to do this assignment and get all of my numbers, right? I mean, you already know the answers, but you're going through the motions of actually putting in the data and understanding, not to screw this piece up right here or this piece right here, So you should be able to get all the same numbers as I get. Yeah. So now the F test, we want to look at their uncertainties. And the null hypothesis is they have the same standard deviation or the same variance. We know that's not true, right? Just looking at the data, we know that's not true. But let's get a number on it. And the F test can tell us. Let's say it was a little more subtle and they looked kind of the same. Let's do an F test and see if they passed the F test. So we calculate F experimental. And this one is nice. It's so easy. It's just a ratio of the standard deviation squared, okay? So I love that. Now, because the F test doesn't tell you which one to put on top and which one to put on bottom, it could be a number greater than 1 or less than 1. And so it's also kind of a two-tailed test. Your F experimental could be a really big number or a really small number. And so we have two criteria to test against. So again, we have an alpha 0.025 because it could be really high or it could be really low. And one alpha is 0.025 and the other is 0.975. So we have to calculate both of those values. So this is, again, one using the degrees of freedom. You see 8 and 9. Where do these come from? Y'all tell me. Yeah, N1 minus 1 and N2 minus 1. All right, so this was 9 and this was 10. So 9 minus 1 is 8, 10 minus 1 is 9. So those are the degrees of freedom for the trainee and for the forensic chemist. Here's the alpha over 2 there. And then so that's the upper critical value for F, 4.1. And then we calculate the lower one. Look at the alpha. So what we're doing is we're looking at sort of a Gaussian curve. Okay, and we're chopping this off at 0.025 and up here at 0.975. And so we're saying if it's out here in these tails, then they're not from the same population, right? So there's a 95% chance they'll be within those two bars, okay? There's only a 2.5% chance they'll be outside either bar. And so if our experimental value is between those two, right, that's what this is. So if this is true, then we do not reject the null hypothesis. If it's greater than the upper one or less than the lower one, we do reject the null hypothesis. So we calculate that. So we take look at this experimental value for this with the outlier, 21, 21.3, and our upper critical value was 4.1. Yeah, so that's pretty bad. All right, and then so our conclusion was, yeah, the F is greater than the F upper, so the variances are not the same. And then for the if we take the outlier out, it improved, but not enough. Okay, we got an improved F value of 8.35, but not enough. So the variances are not the same. And we could tell that from looking at the data. So here's our equations. So these are the null hypotheses we used so far. The trainee and forensic chemist data sets are from the same population. This was rejected because there's statistically significant differences between the means. And that would be the phrasing that you would use in your report, okay? There was this piece in particular. There's statistically significant differences between the means, okay? And then the forensic chemist and the trainee have the same variance. And this was rejected because there are statistically significant differences between the variances. And so this affects the precision. They have different precision. This means they're different from each other, but you could compare them to the true value. I mean, maybe they're both wrong and they're both different, okay? But the forensic chemist was close to the true value. Now you can do this in Minitab. which is a statistical package that you can maybe in the future have access to. The university has a restricted number of seats, but anyway, if you were to have a statistics package like this, it's wonderful because you just go up to basic statistics, two sample t value, put in the data set for trainee and forensic chemist, give me some plots, hit OK, and you get this. And so it's just beautiful. I mean, now I guess you could say it's easy in Excel. You put your formulas in, but it can be a little more tedious in Excel. Here you just menu driven, click, click, click. And this tells us the p-value for the f-test between these two. Now, what do I see? I see a p-value of 0.000. What is that telling me? What's the p-value? Probability of someone else. Probability of. This is taking place of our Kahoot. So it's the probability, we got that, of, scroll back in your notes.
Of the hypothesis being true.
Yeah, the null hypothesis being true. So what's the null hypothesis for the f-test? Yes. And so this is giving us the probability of that. 0. Now, it's not exactly 0 because this is only to 3 decimal places. So you have to say it's less than. What would it be less than before I had to round? Like, when would I have to put a 1 in that place? If the p-value were p equals 0.0005, then I would round that. If I could only keep 3 decimal places, I would round that to 0.001, wouldn't I? So we can say confidently that the p-value is less than 0.0005. Okay. So in this case, it's not just less than 0.05, it's less than 0.0005. I mean, that's all we can say from this. Now, Excel's nice. It calculates the p-values. Like in an ANOVA table, it'll say 10 to the minus 50 or something like that, which is crazy low. And that's what we got in PChem. We won't get that in forensic chem probably. Okay. This also shows some nice things. It shows us the variance. Let's see. No, this is standard deviations. So this is showing us the standard deviation for the trainee right here at say 0.9, okay? And this is showing us the standard deviation for the forensic chemist at 0.2, okay? And what's cool about this is giving us error bars for the standard deviation. So it's saying, given this data, my standard deviation is 0.9, or it might be as low as 0.6, but it could be as high as like 1.9. So that kind of breaks your brain. Normally we have a mean and a standard deviation, which is an error bar on the mean. This is a standard deviation with an error bar on the standard deviation. So, but the main thing you want to look at is notice they don't overlap, right? There's a gap here. And that gap means there's no way, even with 95% confidence, that these standard deviations are the same. Like their uncertainties don't even overlap. And that's why we have a p-value of 0 or less than 0.0005. Okay, so last thing, this is an important thing, it's on the homework too. There's a guide for uncertainty management put on Blackboard. I think it's over 100 pages. I mean, it's a huge document. And it's meant for the lab, like to go into the lab and like make sure that all your analysts and all your procedures are managing uncertainty and all the instruments and everything like that, and how you sample things. And it gives you some equations here for how to calculate the number of samples you will do in the lab. Okay. And so that's the question we're asking here. This is the last thing. I want to go in, I want to analyze this baggie. And in our example, the trainee and the forensic chemist were asked to run the sample 10 times. Okay. Is that valid? Or did I just pull 10 out of someplace? Okay. Right? So why 10? Why not 20? Why not 5? Okay. How many titrations did you do in quant? Like if you were going to characterize an acid or a base? 5? You did 5? That's pretty good, Tedious, isn't it? Yeah. But what was really your limitation? Time. Yeah. I mean, you got a 4-hour lab and time. And even in forensics, time is a limitation. So how do you balance time? How do you balance cost? Because time and cost go together. You're paid a wage. You've got a work day, 2,000 hours for a whole year of business type work. And, are you going to analyze this sample 10 times when 5 would do? You can cut your cost in half. But what if analyzing at 5 produced more error, right? So you're balancing uncertainty. And that's what this uncertainty management concept is about. Okay. So the way this is sort of the rule of thumb distillation of this information. So you inspect and sort the incoming evidence. And in a future lecture, we'll have like 3 different seizures that look a little different, and we're kind of determining if they're the same thing. So like you open a trunk, you got a box full of little baggies of cocaine. You think it's cocaine. You need to analyze that. You got red, green, and blue baggies. Is it the same stuff and they just bought different colored baggies, or are the colors significant? We don't know. Okay. So we're going to treat those as 3 different populations, and we're going to analyze them separately. Okay. So that's what we mean by inspect and sort the incoming evidence. So we had, say, 30 bags, but now we have broken them into groups of 10, 3 groups of 10. And this is saying, since it's only 10, we're going to go ahead, and here's the bottom line. We test all of the bags up to 20. When we get to 20, the diminishing returns, start to play in. We're burning too much time and too much cost. And so then we'll test 10% of the remaining field samples. So this is more conservative than just the 10% rule of thumb. So this is our equation for determining how many samples we do in the lab. If we have that situation where we had 30 samples, we would test 20 randomly, and that would leave 10 more, and we'd take 10% of that. What's 10% of 10? Just 1. So we would do 21 samples out of those 30 bags. But unfortunately, we got 3 different colored bags. And so we're going to treat those as 3 different seizures. We're going to have the red, the green, and the blue bags, and we're going to have to test all 30. We're going to do 10 out of the blue, 10 out of the red, 10 out of the green, and we'll have to do 30 analyses because there's something visually different about them. Okay? What if they're all clear bags and we look at the samples under, good lighting, and we're like, well, these are off color and these are bright white. Okay? There's a visual inspection. That's what that means up there. Inspect and sort. We're going to say, let's pull these yellow ones off and the white ones. Maybe we have 50 white ones and 20 yellow ones. Well, we're going to test all 20 of the yellow ones, but how many would we test of the 50? Okay. Take out the first 20 and we have 30 left over. And so what's 10% of 30? 3. So we'll do 23 random bags of the 30 white ones, 23 of those, and we'll do the 10. What was it? It was 20 of the yellow ones. And that saves us a little bit of time, but we're not losing information. So that's the sampling plan that is a good rule of thumb, and it distills. Again, it's pretty conservative. You get into a really high volume lab, you may have a more complex way of determining how many bags to sample. But this is one we're going to use in this course, and that's what's on the homework. All right. Have a good one.